Hi, my name's Dr. Barry Flannery. I'm the founder and CEO here at Xerotech. Welcome to another episode of XT Tech Talks. Today we're going to be talking about battery chemistry. There's a lot of different chemistries out there. You might have heard of lead acid, nickel cadmium, and many other exotic things. The batteries in your remote control are a different chemistry again, alkaline chemistries. But today we're going to focus on the ones that everybody is using in the world today and that they'll be using inside in the future. So lithium ion batteries, the first thing to understand is lithium ion is a family. It's no one thing. There's different types of lithium ion battery cells. And in general, there's 4 different pieces to a battery. So I'm going to be focused on the most common ones, the most commercially available ones on the market. But in principle, there's 4 key elements to a lithium ion battery. So you've got the 4 key pieces. You've got the anode, you've got the cathode, you've got the separator, and you've got the electrolyte. In its most simplest form, you can consider the anode as the positive side, the cathode is the negative side, the separator is what stops plus and minus from touching, and the electrolyte is what enables you to flow current or flow electrons through the separator. So what's important to understand here is that you might see in the news and on the line lots of new developments on batteries, that there's been a fundamental revolution in batteries that's going to change everything. Unfortunately, that's rarely true. What you're probably hearing is that there's been a development on one of these 4 things. So for example, you might have heard about silicon anodes. You might have heard about different cathode chemistries, high nickel, low nickel, high cobalt, no cobalt. So when we hear about the different types of lithium ion batteries, you might have heard people talk about NMC, NCA, LFP. These are the big, most common ones today. And then in some markets, you may have heard of LTO. So these are basically the constituent parts of the cathode side of the battery. So NMC just means nickel, manganese, cobalt. NCA is nickel, cobalt, aluminium. And LFP is lithium iron phosphate. So the acronym is slightly different there. And then LTO is lithium titanate, a different type of very robust chemistry. The reason you've got to be careful with these and trying to say that, oh, it's an NMC or an NCA cell, is modern cell developments are starting to blur the lines between the two. So there's batteries that are NMCA batteries, there's LFMP, there's LFMP with silicon anodes, there's different inorganic electrolytes, there's ceramic separators. This is like baking a cake. When you change any one of these things, or in combination, you change the performance of the battery. And generally speaking, the things that you care about in the battery are the voltage and its capacity. There are some other things in here that may matter as well, that is the lifetime and potentially safety considerations, as well as power output. Some of these chemistries are slightly different and they're better at one thing versus another. So we're going to be taking a deep dive between the 3 most common commercial chemistries on the market today. So that's NMC, NCA, and LFP. And we might do a little note on LTO. So the first thing to understand about the different chemistries is, why are there different chemistries? Why would you want different chemistries? And there's a number of different reasons for that. So we're just going to clean off before we get into it. So as opposed to getting into the deep fundamental chemistry of these ones, I'm going to talk about the real practical commercial reality on the market today. So we're going to talk about NMC, NCA, LFP, and we will make a note on LTO. So we're going to assume a 2170 battery cell for each. So we're just going to grab different chemistries here for the sake of argument. An NMC, an NCA, an LFP, and we don't have an LTO today, but we'll put this one in as a placeholder. So the first most important thing when somebody thinks about a battery, they care about one of 2 things. They either care about the energy stored or the power output, generally speaking. So NMC and NCA have effectively the same amount of energy in them, usually. So you can usually buy a 5 amp hour NMC cell. and it's typically got a voltage of 3.7 volts. LFP in 2170 format probably has about 3 amp hours, and its voltage is lower. Its voltage is around 3.2 volts. LTO is lower again. It's typically probably 1.5 amp hours, and its voltage is around 2.2 volts per cell. So what that means is, in a 2170, you're probably going to get 18 watt hours in both NMC and NCA, and they both weigh the same amount. They both weigh around 70 grams. The LFP cell will have less. An LFP cell will have about 10 watt hours, and the LTO will vary, but it'll have probably around 4 watt hours. And again, weighing around the same amount. So the big difference here is, as you look at the different chemistries, this is what it's actually like on today's market with cells you can really buy today in cylindrical format. For these same two cells, 18 watt hours. By going to LFP, you're down to only 10 watt hours. So it's a significant amount of energy reduction in the LFP. And the LTO is dramatically smaller again. So taking the most extreme case here, if you had an NMC battery pack that was 100 kilowatt hours, like in a car, for the same size and the same weight of battery pack, you would only have roughly a 25 kilowatt hour LTO battery pack. And the LFP will be somewhere in between, at approximately 60% of the energy. So the LFP will probably be around 60 kilowatt hours. So that's one of the first things you need to consider when choosing a different battery chemistry, is how much energy it has. So if you don't have a lot of space on your machine and you need a lot of energy, well then you're almost forced to go down to the higher energy density chemistries. So that's what we talk about when we say energy density. There's gravimetric and there's volumetric. Gravimetric is how much energy in a given unit of weight you have. So obviously if you've got 18 watt hours here and it only weighs 70 grams, that's a much better number than having 4 watt hours weighing 70 grams. And in this case here, you can see that these all have the same size. They're 2170. So that means there's 21 millimeters diameter, 70 millimeters in height. So the volumetric energy density is going to be better with the high energy density chemistries, as is the gravimetric energy density. So you might ask, why would somebody use an LTO battery cell versus an NMC? LTO has low energy density because it's got an extremely stable and robust cathode. That's a good thing and a bad thing. The bad thing is that it has really low energy. The good thing is that it's nearly indestructible. It's got incredibly long cycle life, tens of thousands of cycles versus only 1,000 or 2,000 cycles for these chemistries. And it's also able to charge and discharge extremely aggressively. You'll have recalled in an earlier video we talked about C rates. NMC chemistries and NCA chemistries can only really do a couple of C typically. Power cells, a specific variant of these, can do higher C rates, but LTO can do 10C, 20C, 50C because it's so robust and stable. LFP is somewhere between the two, but it's much closer to NMC and NCA compared to LTO. So if you're to look at a scale here of cycle life, you would have LTO down here, you would have NMC and NCA down here, and you would have LFP here. So LTO is dramatically stronger than the other two cells. Some people might say it's safer, but you always have to be careful when we talk about battery safety. It has a higher temperature that it must reach for it to thermally run away and catch fire. Almost impractically high, which makes it very rare for this to happen with LTO. but it can burn. And something I tell everyone in the battery industry is all battery cells can burn, given the right conditions. But with LTO and LFP, they're more robust in terms of a nail penetration or a crush or abuse conditions. They're less likely to result in a thermal runaway. Whereas NMC and NCA have lower stability, meaning that if they reach a certain temperature, a thermal runaway temperature, around 150 degrees Celsius, they can catch fire and burn. Whereas for LFP, it's a couple hundred degrees, and LTO is even higher again. So another important aspect of battery cells and chemistry is the way they charge, the way they discharge, and the nature of their voltage curves. So if we look at our common chemistries here of LFP, NMC, and NCA, for the purposes of this, are effectively the same. A battery has a voltage discharge curve. And if we remember, the capacity of a battery cell is amp hours. It varies from chemistry to chemistry what that voltage curve looks like. But for an NMC cell, it might look a little like this, where the battery is defined as fully empty down at 2.5 volts. It's completely full at 4.2 volts. And in fact, some chemistries can be a lot steeper than that there's a quick drop off in the 4.2 volts and then linearly dropping down. We say that the nominal voltage of a battery is 3.7 volts because most of the average capacity is here. So this is capacity and this is voltage. So if we say there's 5,000 milliamp hours, that means that the amount of capacity under this curve to this point here is 5,000 milliamp hours. So if you were to discharge the battery from 4.2 volts down to 3.7 volts, you'd have used, in this case, about half of the capacity. Again, it will vary from cell to cell, from manufacturer to manufacturer. For different chemistries, particularly LFP, the curve is quite unique in that it's incredibly flat. An LFP curve will have 3.65 volts as its maximum voltage, a nominal voltage of 3.2, and a cutoff voltage of 2.5. But what's unique about LFP is that this curve is nearly completely flat on its nominal voltage. So as you discharge it, it will be almost flat and then roll off the end. So this is what makes it quite challenging to use as a battery cell. It's good from a performance perspective because when the battery is being used, charged, and discharged in normal operation, you don't see a change in performance. In an electric vehicle like a long-range Tesla, you will notice that when the battery is 100% charged, you actually have more power because the voltage is higher. When the battery is nearly full, the voltage is almost 4 volts per cell, or 4.2 volts. And if you've got hundreds of cells in series, which we'll come to in a moment, it means the pack voltage might be 400 volts versus 250 volts. And remembering our power equation, power is voltage by current. If this voltage is twice as high for the same current, you've twice the power. So that's important. For LFP, it's very uniform. And that actually makes it quite challenging to even know for an LFP battery how much energy is in the battery, because measuring the voltage doesn't really tell you a whole lot, because it's like reading the voltage here that it's 3.2 volts here, and it's still going to be 3.2 volts here. The reality is you would need to measure that it's 3.231 here and it's 3.201 here. But that's still a very small voltage difference, so you need very high precision measurement to understand the difference between the two. So in our battery management systems, we use a different method for calculating the voltage there, or a combination of a few. We're actually counting the amount of amps that flow at any one time. It's called Coulomb counting. And then we'll switch back to voltage estimation in different parts of that curve. The other important thing to understand with lithium-ion batteries is these limits of voltage. These are incredibly important. If a battery cell voltage drops below 2.5 volts, it is empty, it is zero. So the gauges that you have on your phone, on your car, in your wherever it might be. This is 0% SOC, state of charge. This is 100% SOC. So that's the state of charge. The reason you should never ever go below 2.5 volts and why we have something called a battery management system is that you cause fundamental electrochemical damage to the battery. There isn't really energy below 2.5 volts. You actually start to damage the cell. It starts to dissolve and many bad things inside of it start to happen. Similarly, when the voltage goes above 4.2 volts, you start to run into new electrochemical faults and issues. So it's incredibly bad and incredibly dangerous to go above 4.2 volts per cell or to go below 2.5 volts per cell. So as you go high, you start to do something called lithium plating and creating dendrites in the battery, which can lead to short circuits, thermal runaways, and many other very dangerous effects. So that's why it's vitally important that you have a BMS that controls the voltage, controls the temperature, and controls the rate that you charge and discharge that battery. The next thing we might talk about with the battery cell is that as we talked about our resistances here, you might recall that the energy lost in a battery is I squared R. A battery is not a perfect store of energy. A battery basically has a tiny resistance inside of it that limits the amount of current that can flow. And what that means is when you put a battery in a circuit and let the voltage drive a current around it, you'll actually see the voltage on the terminals drop. So if you've ever seen in the movies or maybe for your own car, when you turn on the engine and you're cranking that engine and the alternator, you'll see that the battery voltage drops. You'll see the headlights dim for a second. What's happening there is that a huge amount of current is flowing out of the battery to crank the engine, to turn it on, the starter of the engine. And that's driven by the internal resistance of that lead acid battery. So if we were to look at our curve here, this would be what would be called the open circuit voltage curve, or a very low current flow. But if you put a load on the battery, for example 1C, it'll cause the curve to be pulled down and different. It'll be a lower voltage under the same load. So even if the battery is full, the voltage will drop. So that could be 1C. If you go to 2C, again, it'll drop and be a different curve. If you go to 10C or more, it'll drop down lower. And if you try and do 50C or 100C, it'll be below the minimum voltage. It simply can't do it. There's a fundamental limitation of how much a given battery cell can discharge before the voltage drops below its minimum cutoff voltage. And that's really important to understand, because what you can see here is that depending on how full the battery is, you won't be able to do certain amounts of charges or discharge rates for a given load. So that means if you look at a data sheet for a Xerotech battery, we have something called a power map. That power map is basically showing you that if the battery is at 20% state of charge, so if it's close to being empty, you won't be allowed to do a heavy discharge on that battery because it's going to pull it below that 2.5 volts per cell. And the exact same is true of charging, it's just reversed. So if you want to charge a battery, you actually get something called a voltage rise. So the terminal voltage will want to rise in that case. So you'd have a different curve going up the way. So if a battery is nearly empty at 0% state of charge, you could charge at very high C rates because it's able to increase the voltage up high below this maximum voltage curve. So that means that when the battery is nearly full, up in this range here, you have to dial back the current. So that's actually very interesting that if you look at a modern electric car, when we say something can charge in 20 minutes or you want to do a 2C fast charge, it's not actually doing a 2C fast charge. For example, a Tesla at a supercharger might have a charge curve that starts off low, gets very high, and then tapers off, down like this. And this peak here might be up on 3C, but then rapidly tailoring off because the voltage and the state of charge of the battery is increasing rapidly as it goes up here. So as it's nearly empty, it can take huge amounts of power in this region here. But when it's nearly full, it can take less and less power. So that's important for batteries and how you use them, because you'll be able to fast charge a battery usually from about 0 to 80% in a very short period of time. It could be 20 minutes, could be 30 minutes, because of these characteristics of battery cells, that the internal resistance, the terminal voltage of the battery, and staying below the fundamental limits mean that you can accept much higher currents. And the last piece that's very important with batteries is that the temperature also has a big impact. So if we're to get rid of one of our curves here for LFP, and if we're to plot a curve of a battery cell, of the internal resistance, remember that number there, that's the internal resistance. And if we're to do that as a function of its capacity, when the battery is nearly empty, you actually get an internal resistance curve that looks like this. So when it's nearly empty and when it's nearly full, its internal resistance is changing. We said previously that a typical internal resistance of a battery can be about 30 milliohms, but it can go much higher. When that cell is nearly full, it can be nearly 100 milliohms. And this is assuming 25 degrees Celsius. If the battery was at minus 20, for example, the internal resistance could be dramatically higher than before. This is what makes managing batteries quite complicated, and that's why something like a battery management system exists in the first place. Because this curve, how much power you can give me, it depends on the internal resistance of the cell, because that determines the voltage drop as per this equation. But that internal resistance, not only does it vary depending on where you are in this curve, on the state of charge window, it also depends on temperature. So if the battery is hot versus cold, you've got lower internal resistance when it's hotter, because it's electrochemistry, it's like something that's living. Every 10 degrees Celsius above 25, you're roughly doubling chemical reaction rates, the good ones and the bad ones. So the good ones are basically the ones that deliver power. As it gets hotter, the chemistry is more reactive, the ions and electrons are more mobile through the separators, so that results in a lower internal resistance, higher power output. But it also accelerates the bad chemical reactions, the ones that age the battery cell. So when you charge and discharge a battery up and down constantly, you don't end up with the same amount of power after each cycle. So what we defined before as 100% SOH, state of health, over time, as we do more and more cycles, it starts to decrease and drop off. And we say a battery is at end of life when it reaches 80% SOH. Some manufacturers define it as 60, 70% SOH. And this could be for an NMC cell, could be 1,000 cycles, could be 2,000 cycles. What's important to understand is that as this battery ages, as it goes further down this curve, the internal resistance is also changing as well. So the algorithms get quite complex in terms of how to manage that battery, when all you want to do is how much power can I have? How much energy is left in it? It's constantly changing as a function of internal resistance, temperature, state of charge, open circuit voltage, state of health. So that's why we do a lot of work, for example, here at Xerotech, that we have to characterize battery cells, charging them on all sorts of different profiles at different temperatures and different voltages to understand the best way to use those batteries for a given application. So in general, you can't mix different battery cells, different chemistries, because they have to have the same voltage between the two. So if this was an LFP and this was an NMC, and if we say that they're both at 100% state of charge, if you get a multimeter and measure these, this one's going to read 4.2 volts, this one's going to read 3.65 volts. That's very important, because if you were to then connect these together with a wire on the same bus, what would end up happening here is this, because it's at a higher voltage than this, would flow current into the other one. In fact, it's worse than that, because recall when we said the internal resistance of a battery is quite low, it's about 30 milliohms. But for the sake of making some easy numbers, let's say it's 10 milliohms, which would be very typical for a power cell on the market. If it's 10 milliohms, this voltage difference here, it's about 0.5 volts, roughly speaking. So the amount of current that would flow from this cell to the other one will be 0.5 volts divided by 10 milliohms. That would be 50 amps. That's a huge amount of current that would flow between the two, because when we talked about our C rates, these are typically for NMC is 5 amp hour. That would be discharging that 5 amp hour cell at 10C. It'd be a huge discharge on this. That's why you can't mix battery cells together of different chemistries. There are some companies today offering this, but what they do is they've got a special piece of power electronics that deals with the voltage difference and manages it. This is also the reason why you never want to put very different voltage batteries of the same type in parallel at different voltages, because you'll get a huge flow of current from one to another. And in fact, if you have an entire battery pack, it's even more dangerous, because you've got thousands, if not tens of thousands of battery cells in parallel. And this resistance is very low. 10 milliohms could be the resistance of an entire pack. And as opposed to having 500 millivolts or 0.5 volts of potential difference, imagine connecting two 800 volt packs together, and one of them was nearly empty, that 400 volts. And this one had 600 volts. If you have a 200 volt difference between these two packs at 0.01 milliohms, that's a massive amount of current. That would be 20,000 amps of current. It would incinerate the wire that you connected between those batteries. It would blow the fuses in the batteries. So that's why you have to be very careful with batteries. Even though they're low voltage, if you put a battery in short circuit, which is quite similar to this. So when we say the voltage difference here is 4.2 minus 3.6, around 0.5 volt, when you short circuit a battery, putting a wire from plus to minus, that's basically exposing it to a voltage difference of the full terminal voltage of 4.2 volts. So if you took 4.2 volts divided by 0.01, that battery cell will try and deliver 400 amps of current out of it. So if we took a wire on this battery cell, small thin wire, the wire would glow white hot and burn straight away, because there's 400 amps flowing through that wire. And remember our first equation, I squared R. If you have 400 amps going through that, that would be hundreds of watts, thousands of watts potentially. And that wire can't carry that much energy or heat, because it'll heat up the wire and it'll then melt and incinerate it. So that's why it's very important to not short circuit a battery with a piece of wire. And actually putting another battery in parallel with a battery that's not at the same voltage, because the other battery has such a low internal resistance, it's almost like a short circuit. So you have to be very careful when you do that. So the reason lithium ion is becoming so popular now, and we're seeing it in lots of vehicles, it comes down to the energy density. Back to when we talked about the different battery cells of being 18 watt hours, 10 watt hours, and maybe 4 watt hours for LTO, they were just within the lithium ion family. Obviously, previous battery technologies like nickel cadmium, or NiCads, and lead acid batteries, they had very low energy densities as well. Somewhere in this region, if not lower again. So the problem was you just simply couldn't put enough energy into the vehicle, both volumetrically and gravimetrically. So if you were to make an electric car with lead acid batteries, it would have a range of 50 miles and it'd probably weigh hundreds and hundreds of kilograms, if not much more than that. So the reason lithium ion is becoming so popular is this high energy density, high power density, and the cost has come down dramatically through mass industrialization. One final point that's incredibly important for batteries, particularly lithium ion batteries, most battery cells do not want to operate above 60 degrees Celsius or below 0 degrees Celsius. So when you go below 0 degrees Celsius for a battery, you're able to discharge it at a much lower rate, but you can't charge it. So you basically can't charge most conventional chemistries available on the market below 0 today. This has to do with an electrochemical fact inside of the battery that you cause lithium plating on the battery. So if you've got, in a very simplistic way of understanding it, a plus and a minus inside of the battery and a separator, the ions flow from one side to another in the battery, and they accumulate inside of the battery anodes and cathodes, for want of a better word, in a cave structure. If you try and charge this battery below 0, instead of them going into the caves, the lithium ions, they tend to plate on the surface. It's like having a sponge, but they cover all the holes in the sponge. It causes lithium plating. So that does two things. It massively reduces the capacity of the battery. So if you were to charge a battery aggressively below 0 at -10, you might lose 20% of the capacity straight away. It's irreparably damage that battery. The second thing it does is when this plating happens, it tends to grow crystals of lithium metal, and they're called dendrites. They look like Christmas trees, and these can grow all the way through. In some cases, they could punch through the separator. This distance is much shorter in the real world, and they could actually bridge all the way to the other side of the cell, creating an internal short circuit, which is extremely dangerous. It could cause internal heating, and that wire, like our previous example, is very low resistance, and there's a voltage difference between the two. So you'll get a flow of current, a high flow of current, a lot of heat. And that heat will cause burning of this plastic separator, burning of this combustible electrolyte inside of the battery. So it's really dangerous. And also, even if you don't puncture the separator, you could have a jagged dendrite Christmas tree here that if the battery is shocked or abused like this, it might be enough to mechanically puncture through the separator. So the cells could be dangerous and unstable in use after that. So all BMSs, like the Xerotech one, will prevent you from charging below 0 degrees Celsius. When it comes to discharging, that's okay. You can discharge below 0, but your power output will be significantly reduced. And that comes back to our DCIR curve, our DC internal resistance. You might remember this bathtub type curve here. So this is going to be across the SOC window. At lower temperatures, this curve is much higher. So basically the batteries have high resistance. And when they have high resistance, it limits the amount of capacity they have. It limits the amount of power they can discharge until they heat up. But as the battery is discharging from this cold condition, it tends to self-heat. So temperature is incredibly important in terms of batteries. You can't charge below 0, or else you could result in this dangerous lithium plating or thermal runaway condition. So that means you have to heat the batteries up to be able to use them below 0 in cold ambience. That's why thermal management of battery packs is so important. The second piece is when batteries are cold, that high DCIR massively reduces power output. So you can't get the power out even if you wanted to. When batteries are hot, the opposite is true. Actually, a hotter battery will have a lower DCIR curve. So ironically, they have even more power output. They have more capacity. So if you took a battery at 100% state of charge at 25 degrees, and if you heat it up to 60 degrees, it'll have 105% capacity, and it'll actually have more energy because of that lower resistance. But the danger with high temperatures is that there's a certain temperature that becomes close to a thermal runaway condition, that the battery gets so hot that if you run the risk of melting this separator, which is basically a piece of plastic that melts at a few hundred degrees or 100 degrees, 150, it causes a direct internal short of the battery, self-heating, self-thermal runaway, heat generation, causes fire. But batteries can and do operate well at high temperatures. But the negative effect is it massively reduces lifetime because there's good chemistry, the flowing from this side to this side through the separator, but there's also bad chemistry. They're the irreversible chemical reactions that lead to capacity fade and degradation. So the internal resistance starts to climb over time as you get more and more cycles on the battery, and as that SOH starts to decrease down to a certain level. That's coming from an increase in DC internal resistance. So you don't want to keep a battery at high temperatures all the time. It will reduce lifetime very significantly. So every 10 degrees C above 25 degrees, battery life is roughly speaking halved, cut in half. So that's really important. Controlling the temperature of a battery is the #1 thing to do to be able to use it across the wide range, to ensure it's safe and to maximize lifetime. The best thing to do for a battery typically is to keep it at around 25 degrees C. So that pretty much concludes our video today, giving you an overview of all the different practical aspects of battery cells and battery chemistry on the market today. Thanks very much for listening.